We're going to talk about fundamentals of control theory, which have tremendous applications in laboratory settings and pretty much anytime you're running experimental dynamics and any kind of experimentation. And to do that, we're going to start off by writing down the state space formulation that we are familiar with so far. We have the ABC matrices, and we've done videos on this. And so we take this time domain manifestation and convert it to Laplace domain. And in Laplace domain, we're going to have initial conditions. And here's what the state equation is going to look like. And the output equation looks as follows. There it is. Now we are going to take this equation and manipulate it such that we have all the x's on the left-hand side, and it's going to look as follows. X of s is equal to, there it is. And lastly, I move everything else besides the x of s to the right-hand side, and this is what I'm going to have. I'm going to have a bunch of inverted si minus a's, and I'm going to talk about that in a second. So this is pretty important. All right, so we're going to fit this here. And really, what's special about the term in the brackets that's inverted is we typically call this a state transition matrix, and it's defined as follows. It's described typically by a phi, and it's inverted. And really, this carries all the eigenvalues and all the natural frequencies that a dynamical system has. So if I were to rewrite my x of s, it would look as follows. Now, phi of t was written in Laplace domain, and what I can do is I can do the inverse Laplace and get my phi in time domain, and we're going to call it the state transition matrix so we don't forget about this. Here it is, and we're going to move all of this over. And pretty much we can find the solution to the dynamical system, meaning we can find x of t's, and the general solution is written as phi of t initial conditions x naught plus whatever the input forces are. They become part of this convolution integral, which looks like this, u tau d tau. And so if you have all these parameters, you could plug them in. Then you can find your x of t's, meaning your states in time domain. And so what we're going to do first is we're going to take the A matrix, diagonalize it by multiplying it by its eigenvectors. Those p's are the eigenvectors. And we are going to find phi bar, which is going to have the following shape. So it's going to be diagonal as well. And lastly, we take phi bar and multiply it again by the eigenvectors that we had found earlier to identify the actual phi, which is the state transition matrix. Anytime you're interested in identifying the analytical solution to the state space formulation, these three formulations are what you need to look at. So now I'm interested in the stability of my dynamical system, and pretty much I have to look at the eigenvalues that I have. These are the lambda 1s through lambda n. And if I look at the real values of these lambdas and they're greater than 0, then I'm dealing with an unstable system. If these are equal to 0, and my system is lightly nonlinear, then I can't really make any inferences from the lambda. If my system is fully linear, then the system is kind of stable. If the lambda is less than 0, then my system is definitely stable. So anytime lambda is equal to 0, I'm going to leave it as sort of. It really depends on the physical system. So, you know, it oscillates like this, and for a stable system, we have convergence, kind of like that. Now, I'm going to take the state space formulation that I had, and I'm going to use the state matrices to write out what the transfer function equivalence of that system is going to look like. And this is the relationship we use. We can have this kind of numerator, typically for any number of zeros. Zeros are the roots of the numerator, and in the denominator, this is what I'm going to have. Here we are. And so again, if I'm interested in the numerator and I want to find the roots of the numerator, what I identify is the zeros of my transfer function. And at the same time, if I find the roots of my denominator, what I'm getting are the poles of my transfer function. We're going to call these poles. And pretty much anytime I'm interested in my stability, I just have to look at my poles. Poles are what determine the stability of a dynamical system. So I set ds to 0, and I find my roots. If they're positive, the system is unstable. If they're negative, then the system is stable. So let's do an example now. We are given a dynamical system or a transfer function that looks like this. Here it is, 5s plus 6. And what I'm going to do is I'm going to factor the denominator so I can see the poles. And here we are. So if I set the numerator to 0, what I'm going to get is that my 0 is equal to minus 1 over s. So let's choose a color. Here it is. 0 is minus 1 over 2. And the pole is, we have two poles. One is minus 3. The second one is minus 2. Since both of these are negatives, what I can say is my dynamical system is stable. Now, besides stability, there are two important concepts we have to look at. These are controllability and observability. Controllability states that in order to be able to do whatever we want to a given dynamical system under control input, the system must be controllable. And observability states that in order to see what's going on inside a system under observation, the system must be observable. So these are very important concepts along with stability that we're going to pay a lot of attention to in this lecture. So if I'm given a dynamical system that is free of inputs and it has an initial condition that looks as follows. It's going to be xt naught is equal to x naught, and here's the dynamical system. Cux of t. Now what I can do is I can take the output of the system and shift it in time. And shifting in time or in discrete time is analogous to a derivative in continuous time. So every time I'm taking a derivative, I'm actually shifting in time. So my second derivative will have the following shape. That will be cx double dot t naught. And you know, this can go on forever. So we're going to package this, move it up here. Let's see. And really the byproduct of this whole thing is we can take these derivatives and we're going to package them such that we have all these derivatives in a single vector. So these are our outputs. And you know, you could have n-1 many derivatives. Let's package it under a vector. And this whole thing is going to equal a vector of C's and A's. Now this vector is important because we always use it, and is typically referred to as the observability matrix. And it's multiplied again by the states. And we have the observability matrix multiplied by the states, and we get the outputs. An important theorem that we need to discuss here is that a linear continuous time system with measurements is observable if and only if this observability matrix has a full rank. So if I figure out what the rank of this O matrix is, and it's equals n being the dimension of the A matrix, then this system is full rank and it's fully observable. If it's not full rank, then it's partially observable, meaning some of the states we cannot see. So we're going to move this up. Now there is a similar concept for controllability where we end up with a C matrix. This is large C, and this matrix is comprised of B's and A's. And the theorem here states that a linear continuous time system is controllable if and only if the controllability matrix C has a full rank. So again, if rank of C is equal to n, which is the dimension of the A matrix. And if this is true, then we have complete controllability, and otherwise it's a partially controllable system. Okay, so let's move this out of the way. Now, besides the stability, observability, controllability concepts that we talked about, there's another very important concept that we need to pay attention to, and it has to do with feedbacks and really this whole notion of pole placement that we hear so much in control theory. To do that, I'm going to start off with an example where I have this state space formulation. I got this A matrix, which is diagonal, very easy to work with, and this is what it looks like. And by the way, with diagonal systems, your diagonal terms are your eigenvalues. And this is what our output looks like. Now, what I can do is I have this dynamical system. I can introduce a control to it, a control action to it. And so we're going to define a control. And this control will be equal to u is equal to minus kx plus r. And x here is our state. K is some sort of gain, and R is some arbitrary input. And so this is what my updated state space formulation is going to look like. A is going to be augmented to a closed loop. And so we call this linear state feedback. This is a very typical form for state feedback. And if I were to draw this in a more schematic way, what I could say is, I have, let's see, I have my dynamical system, my ABCD matrices, and we're going to draw it here. And the input to this dynamical system has the following format. It has the reference R, it has this feedback term K, and the states go into that. They get multiplied by K. And this is what the schematic of a feedback loop looks like. So that's what we're interested in. Now, what I can say is my original A matrix has 3 poles. And this should be very clear to you. We have a 3x3 system, so we should have 3 eigenvalues. Lambda 1 is equal to 1, lambda 2 is equal to 2, lambda 3 is equal to minus 1. Now, it turns out that the first lambda is controllable and observable. And I'll tell you in a second how we figure this out. The second lambda is controllable, but it's not observable. And lastly, the third lambda is observable, but not controllable. And what I use for this sort of assessment is this test called the Hottis-Rosenbrock test. I'm probably not pronouncing it correctly, but this is what it looks like. And so, you could always Google this, and it will show you how to do this kind of testing to figure out which states are controllable and which states are observable. The controllability matrix in this for this example will be as follows. It will be like this. And if you look at the rank of this, of course it's equal to 2, and the observability matrix will have the following form. And again, if you were to do the rank of this, it would also have a rank of 2. An important note here is that controllability and observability are not intrinsic properties of the dynamical system. Whether the model has them or not depends on the representation that you choose. So if I had a different state space formulation representing the same system, I could have a different result. Now, I'm going to list my closed loop A matrix. This was the augmented matrix that we figured out earlier due to the state feedback action. And here's what it's going to look like. And pretty much, I'm going to take this A matrix and do controllability, observability, and stability analysis. For controllability, when I find my controllability matrix, this large C, what I'll get is a system that looks like this, that has this controllability. Now, I haven't gone into the details here, but this system has a rank of 2 regardless of what the k values are, what k1, k2, and k3 are. And the conclusion that we can draw here is that the rank of the controllability matrix is completely invariant under state feedback. So if I have a feedback system, it's not going to do anything to my controllability. It's not going to make my system more controllable. That is one important conclusion. When it comes to observability, however, these feedback actions in fact do matter. And here we're going to draw our observability matrix. It will look like this. This is quite a big matrix, and it will be comprised of these 3 Ks. And so you can go ahead and put in different K values, and each time you're going to get an observability matrix that has different ranks. So I can say the rank of my observability matrix. So actually, let's move this up a little bit so we have a little bit more room. So what I can say is the rank of my observability matrix could be 1, 2, or 3, depending on the k parameters that I choose. So if I say k is as follows, k1 is equal to 1, k2 is equal to 0, k3 is equal to -1, I'll get at a rank of 1. And if I set all of them to 0, my rank is 2. And so forth. I can do all kinds of manipulations here. So here the theory states that observability is not invariant under state feedback. So state feedback can make my system observable. That's the conclusion here. And lastly, we're going to talk about stability of the system. And to do that, we just have to take the determinant of the augmented closed loop A matrix, and what we're going to get is the following. And really what you're noticing here is that lambda is equal to -1 is not affected by k1 and k2, whereas the other lambdas are in fact impacted by k1 and k2. And what this is really stating is that the poles or the lambdas that are controllable can be manipulated to have to change the stability of the system, whereas the lambdas that are not controllable we cannot really do that with. So the theory states that arbitrary pole placement is possible by linear state feedback in the controllable subspace only. In the controllable subspace only. So that's another important conclusion to draw here, and here it is. Another very important concept in control theory is the idea of observers. If I have a dynamical system and, for instance, I only know what the inputs and outputs of that dynamical system are, I don't know what the states are, then what I can do is I can design an observer which is going to predict my states for me. And the observer will have this following formulation. It will just be another dynamical system. So if I were to do this schematically, I would have my own, my original dynamical system, P of S. I know what the inputs and outputs of the system are. I design myself an observer which will take the inputs and outputs to my original system, and it will estimate what my states are. So that's what an observer does, and it's really useful. So we can make an observer in the following form. This is the observer equation. So we have x hat, and L here is the observer gain. And we define an error term, and the derivative of the error term will be the original states minus the estimated states. And I can write the original state space minus the estimated state space. with the added gains. And this system can be summarized as follows. It's A minus LC E, E being the error between the original state and the estimated. And so the idea here is to take the difference between the real and estimated states, which I've described as x tilde here, and we want x tilde to go to 0 as time goes to infinity. And that's really the goal. And so if I have an AC pair, which is observable, what I can do is I can place my observer poles. I can design the L gain, or the observer gain, so that the eigenvalues of A minus LC is Hurwitz, or they are stable. And what that means is that my error will go to 0 with time. That's exponential decay. All right, see you next time.